Ever wonder why the world works the way it does? A lot of it traces back to 6 years between 1939 and 1945. Subscribe, and we'll break down the real stories behind the warfare, leadership choices, and ripple effects that still shape our daily lives. The year is 1972. Somewhere in the Ural Mountains, Soviet engineers are finalizing specifications for what will become one of history's most produced main battle tanks. Meanwhile, in Farmingdale, New York, American designers are doing something that seems completely backwards, building an aircraft around a gun. This is not a story about military glory or strategic genius. This is a story about engineering decisions, about physics, about what happens when two radically different approaches to warfare collide in the desert. One side built thousands of tanks, the other side built a flying gun. The results would challenge every assumption about modern air combat. The T-72 represented the culmination of Soviet armored doctrine. Development began in 1967 at Uralvagonzavod in Nizhny Tagil. The requirements were specific: a tank that could be produced in vast numbers, maintained by conscript crews with minimal training, and operated in conditions ranging from Arctic tundra to Central Asian desert. The armor scheme was revolutionary for its time. Composite armor, a sandwich of steel and ceramic materials, sloped at extreme angles to maximize effective thickness. The frontal glacis plate was angled at 68 degrees from vertical. Basic geometry: a projectile hitting at that angle must penetrate nearly 3 times the actual plate thickness to reach the crew compartment. The turret featured similar compound angles. Soviet metallurgists had developed ceramic inserts that would shatter kinetic energy penetrators on impact, dissipating energy before it could reach the crew. The main gun, a 125mm 2A-46 smoothbore cannon, smoothbore rather than rifled, which sacrificed some accuracy at extreme range but allowed higher muzzle velocities. The gun could fire armor-piercing, fin-stabilized, discarding sabot rounds at 1,700 meters per second. At that velocity, the kinetic energy of a 6-kilogram penetrator exceeded 3 million joules, enough to punch through any NATO tank armor of the period at combat ranges. The automatic loader was perhaps the most controversial design element. Western tanks used human loaders, which limited rate of fire but provided flexibility and a fourth crew member for maintenance and security. The T-72's carousel autoloader sat in the turret floor, holding 22 ready rounds, with projectile and propellant charge paired together. This reduced crew to 3 and allowed a depression angle of 5 degrees maximum, but it enabled a sustained rate of fire of 8 rounds per minute, regardless of crew fatigue. The design philosophy extended to every system. The engine, a V12 diesel producing 780 horsepower, simple enough for field maintenance. The suspension, torsion bars that could be replaced with basic tools. The tracks, all metal, no rubber pads that might fail in extreme cold. The fire control, analog computers and coincidence rangefinders that worked without complex electronics that might fail under electromagnetic pulse conditions. By 1991, over 25,000 T-72 tanks had been manufactured across the Soviet Union, Poland, Czechoslovakia, Yugoslavia, and India. It was the Kalashnikov of armored vehicles, not the most sophisticated, not the most capable in any single metric, but cheap, reliable, and producible in numbers that could overwhelm through sheer mass. The American approach emerged from a different set of assumptions. NATO war games in the late 1960s consistently showed Soviet armored formations outnumbering Western forces by 3-1, potentially 5-1, in any European conflict scenario. Traditional close air support relied on fighter bombers dropping iron bombs or firing unguided rockets. Multiple passes required, high exposure to ground fire, limited effectiveness against moving armored targets. What if the solution wasn't bombs at all? What if you could shoot tanks the way fighters shot down other aircraft? The concept required a gun that could penetrate tank armor from above, where protection was weakest. The top armor on a T-72 ranged from 20 to 30 millimeters, but achieving penetration from an aircraft moving at 400 miles per hour at a slant angle from potentially 4,000 feet altitude required extraordinary muzzle energy and rate of fire. General Electric's answer was the GAU-8 Avenger, 7 barrels arranged in a circle, hydraulically driven Gatling mechanism, 30 millimeters in diameter, but the ammunition was what mattered. Depleted uranium penetrator cores, uranium-238, the non-fissile isotope left over from nuclear fuel enrichment. Density, 19 grams per cubic centimeter, 68% denser than lead, 2.5 times denser than steel. Self-sharpening on impact, unlike tungsten penetrators, which tend to mushroom. Each projectile was 11 inches long, weighed just under a pound, and left the barrel at 1,013 meters per second. The kinetic energy, approximately 60,000 joules per round. At a rate of fire of 3,900 rounds per minute in high setting, that meant the gun could deliver over 230 million joules downrange in a 3-second burst. For comparison, the total energy in a gallon of gasoline is about 120 million joules. The engineering problem was immediate. The weapon system weighed 4,029 pounds, fully loaded with 1,350 rounds. The gun itself was 19 feet long. The ammunition drum was the size of a small car. The recoil force approached 10,000 pounds, equivalent to the thrust of one of the aircraft's engines. No existing airframe could accommodate it. Every fighter in the American inventory would have been structurally compromised by mounting such a weapon. The recoil would have torn mounting points out of the wings. The ammunition load would have exceeded center of gravity limits. The muzzle blast would have damaged any engine mounted in a conventional nose configuration. Fairchild Republic's solution was radical. Design the airframe second. Start with the gun and build an aircraft around it. Every other system existed to serve one purpose: get the gun to the target and keep it there long enough to employ. The fuselage was designed around the gun, literally. The weapon was mounted slightly offset from center line to allow the firing barrel to align with the aircraft's center axis. The landing gear was positioned to leave clearance for the gun muzzle. When the nose gear retracted, it rotated 90 degrees to fit between the gun and the fuselage structure. The wings were straight, thick, high aspect ratio. Aerodynamically inefficient at high speed, but highly efficient at low speed. Maximum lift at 220 knots. This wasn't a fighter, this was a gun truck that happened to fly. The engines, General Electric TF-34 turbofans, each producing 9,065 pounds of thrust. Mounted high on the fuselage, widely separated, positioned aft of the wings. The placement was deliberate. High mounting, reduced infrared signature when viewed from ground level. Wide separation meant a single hit couldn't disable both engines simultaneously. Positioning them aft of the wings meant the wing structure provided some protection from ground fire. The air intakes were positioned high and forward, away from debris kicked up during operations from unprepared airstrips. The exhaust was cooled by bypass air before exiting, further reducing infrared signature. Each engine had its own fuel system, its own hydraulic pump, its own electrical generator. total system independence. Then came the armor, the bathtub, titanium alloy, 1,200 pounds of it, surrounding the cockpit in a structure that looked like something from a medieval fortress. Thickness varied from half an inch on the sides to 1.5 inches on the floor, where ground fire was most likely. The front panel was shaped to deflect rounds away from the canopy. The sides extended below the seat to protect the pilot's legs from lateral fire. Titanium was expensive, difficult to machine. The bathtub alone cost more than some entire aircraft. But titanium offered the best strength-to-weight ratio of any practical armor material. It could stop 23mm high-explosive rounds, the standard ammunition for Soviet anti-aircraft systems like the ZSU-23-4 Shilka. It could defeat fragmentation from proximity-fused surface-to-air missiles. It wouldn't stop a direct hit from a SAM warhead, but it would keep the pilot alive through anything short of catastrophic damage. The canopy was bulletproof acrylic, 1.5 inches thick. It could stop 50-caliber armor-piercing rounds from ground fire. Combined with the titanium structure, the cockpit became a survivable cell. The pilot could take hits that would have been fatal in any conventional fighter and still fly home. But armor and engine redundancy weren't enough. The flight control system needed similar protection. The A-10 operated on 3 independent hydraulic systems. Each system could operate all primary flight controls independently. Lose one system, full capability remained. Lose 2 systems, degraded but functional. But what happened if all 3 hydraulic systems failed? This is where Soviet engineers, when they later examined technical specifications, encountered something that seemed almost primitive. Manual reversion. Direct mechanical linkage from the control stick and rudder pedals to the elevator and aileron surfaces. Steel cables running through pulleys, just like aircraft from the 1940s. Modern Soviet fighters, like the MiG-29 or Su-27, had no such system. They relied entirely on hydraulic controls because the aerodynamic forces at high speeds made manual control physically impossible. A pilot couldn't generate enough force to move control surfaces against 600-mile-per-hour airflow. But those aircraft were designed for speed. The A-10's maximum velocity was 439 miles per hour. At combat speeds below 300 knots, aerodynamic forces were low enough that a pilot could manually move the control surfaces with significant effort. The manual reversion system added 600 pounds of weight. It added complexity. It added maintenance requirements. But it meant that even with catastrophic hydraulic failure, the aircraft could be controlled well enough to reach friendly territory. Soviet air defense doctrine in the 1980s was the most sophisticated in the world. It was also the most redundant. The system was designed on the assumption that any aerial platform could be defeated if enough overlapping engagement zones were created. The lowest layer, man-portable systems, the 9K-38 Igla, known to NATO as the SA-18 Grouse, infrared homing, effective range 5 to 200 meters, effective altitude ceiling 3,500 meters. These would be distributed among frontline troops positioned near high-value targets like tank columns and artillery batteries. The next layer, mobile short-range systems, the ZSU-23-4 Shilka, a tracked vehicle mounting 4 23mm autocannons with radar fire control, effective ceiling 2,500 meters, rate of fire 3,400 rounds per minute combined. The 9K-35 Strela 10, vehicle mounted with 4 missiles, infrared and radio command guidance, effective out to 5,000 meters. Medium range, the 2K-12 Cub, NATO designation, SA-6 gainful, semi-active radar homing, engagement envelope from 4,000 to 75,000 feet altitude out to 24 kilometers range. Fast enough to engage fighter aircraft, maneuverable enough to track evasive targets. Deployed in batteries of 3 launchers with dedicated radar vehicles. High-altitude SA-2 and SA-3 systems for strategic air defense. These were less relevant for close air support operations, but they defined the ceiling. Any aircraft above 15,000 feet entered their engagement zone. The doctrine was simple: create overlapping zones where no aircraft could operate without entering multiple threat envelopes simultaneously. Force attacking aircraft into the lowest altitude bands where short-range systems and anti-aircraft artillery had maximum effectiveness. The math favored the defense. Air superiority fighters could suppress some systems, but close air support aircraft working at low altitude would face concentrated fire from systems specifically designed to counter them. By 1990, Iraq had spent a decade building exactly this kind of network. Soviet advisors, Soviet equipment, Soviet doctrine. The Republican Guard's air defense battalions operated SA-6, SA-8, and SA-13 missile systems, hundreds of ZSU-23-4 Shilka radar-guided anti-aircraft guns, thousands of man-portable missiles. Western intelligence assessed it as the densest air defense network outside the Soviet Union itself. The Iraqi army also fielded approximately 5,500 tanks, including 1,000 T-72s with the same armor and fire control systems being used by Soviet forces in Eastern Europe. This would be the test case, the validation or refutation of decades of Cold War design philosophy. January 17, 1991. The air campaign begins. For the first 3 weeks, the mission is strategic. Command and control nodes, airfields, strategic air defenses. A-10 units wait. Their mission requires something different. Ground forces in contact, armored columns moving, troops under fire calling for support. That mission begins February 15th. The tactics were refined over 2 decades of training. Low-altitude ingress, 100 to 200 feet above ground level using terrain masking. WADIS, ridgelines, anything that blocked line of sight to air defense radars. Pop up at the last moment to acquire targets. 8,000 to 10,000 feet, high enough to see the battlefield, low enough to avoid giving long-range SAM systems an easy shot. Roll inverted, acquire target. Roll upright into a 30-degree dive, stabilize. Airspeed 350 knots, range 4,000 feet. Trigger. The GAU-8 barrels spin up to speed in half a second. 2-second burst, approximately 130 rounds downrange. The aircraft shudders. The firing barrel is precisely aligned with the aiming pipper, but the recoil pushes the nose down slightly. Experienced pilots compensate automatically. Pull off target with a high G brake, 5 to 6 Gs, tight enough to defeat tracking solutions from radar-guided guns. Never fly straight through your own attack pattern. Ricochet debris from depleted uranium rounds bouncing off desert hardpan could damage your own aircraft. More importantly, any anti-aircraft system that tracked your ingress knows where you'll be if you maintain heading. The first engagements occurred February 15th. The 23rd Tactical Fighter Wing, operating from King Fahd International Airport, engaged Republican Guard armored columns withdrawing from forward positions in Kuwait. The targets were T-72s and T-55s moving in company-strength formations on highways and desert roads. The GEAU-8 rounds hit from above and behind, where armor was thinnest. Top armor on a T-72, 20 to 30 millimeters. Rear armor, 45 millimeters. A depleted uranium penetrator at 1,000 meters per second went through like paper. The rounds penetrated the engine deck, the turret roof, the rear hull. They struck the ammunition carousel. What happened next was predictable. A T-72 carries 45 rounds of ammunition. 22 in the automatic loader carousel, the rest stowed around the crew compartment. When a penetrator hits a propellant charge or a high explosive round, the result is catastrophic. The ammunition detonates. The blast pressure has nowhere to go except up. The turret weighs approximately 10 tons. In verified instances, T-72 turrets were found 30 to 40 meters from the hull after catastrophic kills. The crew had no chance of survival. Iraqi tank crews had trained against horizontal threats, other tanks, anti-tank missiles from ground positions, infantry with rocket-propelled grenades. Their tactical doctrine emphasized hull-down positions, using terrain to minimize exposure. They understood how to angle armor against direct fire. But the vertical threat axis was something different. There was no terrain feature that protected against an attack from above. Between February 24th and 28th, the ground offensive A-10 squadrons flew close air support missions at sortie rates approaching the aircraft's maintenance tolerance limits. Some aircraft flew 4, 5, 6 sorties per day. Turnaround time between missions, 30 minutes for refueling and rearming. Maintenance crews worked in shifts around the clock. The aircraft absorbed battle damage that would have grounded conventional fighters. One aircraft from the 926th Tactical Fighter Group took over 600 holes in the airframe. Anti-aircraft artillery fire, 23mm high-explosive rounds from a Shilka that caught the aircraft during a gun run. The rounds shredded the right side of the fuselage, hydraulic lines severed, fuel tank punctured. The right engine took multiple hits and lost power. The pilot shut down the damaged engine, activated fuel crossfeed to prevent fire, and switched to the backup hydraulic system. The aircraft was controllable. Damaged, leaking fuel, but controllable. The pilot diverted to the nearest friendly airfield, 300 miles away. The flight took 45 minutes. The aircraft landed with one engine, one hydraulic system, and fuel streaming from multiple punctures in the wing tanks. The pilot walked away. The aircraft was repaired and returned to service. Another aircraft took a direct hit from an SA-7 Grail heat-seeking missile. The infrared seeker tracked the right engine exhaust. The warhead detonated within lethal radius. Fragmentation peppered the engine housing and the aft fuselage. The engine exploded. Turbine blades disintegrated. Fragments severed hydraulic lines and punctured fuel tanks. The tail section looked like it had been attacked with a shotgun. The pilot shut down the destroyed engine, secured fuel flow, and assessed the damage. 2 hydraulic systems still functional. Left engine operating normally. Flight controls responding. The aircraft was 150 miles from base, over hostile territory with multiple Iraqi air defense sites between current position and friendly airspace. The pilot flew the aircraft home. Single engine, degraded hydraulics, battle damage that should have resulted in a bailout and an aircraft loss. The pilot landed safely. Russian military advisors embedded with Iraqi forces filed reports expressing genuine confusion. Soviet doctrine was built on assumptions validated by decades of testing and combat experience. When an aircraft was engaged by terminal air defense systems, man-portable missiles, or radar-guided guns at close range, the aircraft was lost. Even if the pilot survived, the aircraft would be too damaged to return to base. The loss rates for Soviet aircraft in Afghanistan, when engaged by Stinger missiles, had confirmed this. 1 hit, 1 kill. The A-10 violated that assumption consistently. Aircraft were returning with damage, that should have been catastrophic. Engine loss was supposed to mean bailout. Hydraulic failure was supposed to mean loss of control. Multiple penetrating hits to the fuselage were supposed to mean structural failure or fire. But the aircraft kept flying. The redundancy that seemed inefficient from a performance engineering standpoint proved operationally decisive when aircraft absorbed battle damage in combat. The numbers told the story. Between February 15th and February 28th, A-10 units flew approximately 100 combat sorties. The total verified count of Iraqi armored vehicles destroyed and attributed to A-10 units, approximately 1,000 tanks, 2,000 other military vehicles, 1,200 artillery pieces. Some kills were achieved using AGM-65 Maverick missiles, a television-guided standoff weapon that allowed engagement from outside most air defense envelopes. But the majority of kills resulted from GAU-8 gun runs, close range, high risk, maximum effectiveness. The aircraft loss rate, 5 A-10s lost to all causes over the entire campaign. 3 to surface-to-air missiles, 2 to anti-aircraft artillery, a loss rate of 0.06%. For context, during the Vietnam War, the loss rate for close air support aircraft exceeded 2%. During the Yom Kippur War in 1973, Israeli loss rates for ground attack missions approached 5% on the first day of combat when facing concentrated Arab air defenses. The expected loss rate, based on Soviet doctrine and the density of Iraqi air defenses, should have been significantly higher. War games and simulations run by both NATO and Soviet planners in the 1980s consistently showed close air support aircraft suffering loss rates of 1 to 3% when operating in high-threat environments. The A-10's actual loss rate was an order of magnitude lower than predicted. The Iraqi T-72 crews never adapted. Their training had prepared them for tank-on-tank combat. Their fire control systems were optimized for engaging targets on the horizontal plane. The gun elevation on a T-72 was limited to 20 degrees maximum. Traverse rate was slow, designed for tracking ground vehicles. Engaging a target at 60 degrees elevation angle, moving at 300 knots, in a dive attack lasting less than 5 seconds, was beyond the system's capability. Some crews attempted to engage A-10s with their main guns during attack runs. There are reports of T-72s firing main gun rounds at attacking aircraft. The probability of hitting a maneuvering target at 4,000 feet range, moving perpendicular to the line of sight, with a weapon system designed for a completely different engagement scenario, was effectively zero. No confirmed hits were recorded. The anti-aircraft systems achieved some success. The 5 A-10s lost represented successful engagements by SAM systems and radar-guided guns, but the loss rate was far below what Soviet doctrine predicted. The redundancy, the armor, the simple, robust systems all contributed to survivability that exceeded theoretical models. The engineering philosophy that produced the A-10 contradicted nearly every trend in military aviation during the 1970s and 1980s. The era of fourth-generation fighters emphasized speed, altitude, and technological sophistication. The F-15 Eagle, designed for air superiority, could exceed Mach 2.5 and operate at altitudes above 60,000 feet. The F-16 Fighting Falcon was designed for agility with a thrust-to-weight ratio that allowed sustained high-G maneuvering. Both aircraft represented the cutting edge of aerospace engineering. The A-10 was the opposite. Maximum speed, 439 miles per hour, slower than a World War II P-51 Mustang. Service ceiling, 45,000 feet, but it operated below 10,000 feet. Thrust-to-weight ratio, 0.36, barely sufficient for level flight at combat weight. The aircraft couldn't outrun threats. It couldn't outclimb threats. It couldn't outmaneuver threats in the traditional sense. What it could do was absorb damage and continue fighting. The bathtub armor weighed as much as a compact car. The manual reversion system was technologically outdated before the aircraft entered service. The gun produced recoil forces that required the entire airframe to be structurally reinforced. The design trade-offs reduced performance in every traditional metric. But those trade-offs bought survivability. The T-72 represented a parallel philosophy from a different direction. Soviet designers optimized for mass production and adequate performance across all categories. Not the best armor, not the most accurate gun, not the most sophisticated fire control, but cheap enough to produce in thousands, simple enough to maintain with minimal training, robust enough to operate in harsh conditions. The design philosophy was sound for its intended purpose, overwhelming NATO forces through numerical superiority in a European ground war. But that war never happened. Instead, the T-72 faced an opponent it wasn't designed to fight, using tactics Soviet designers hadn't anticipated. The low-profile silhouette that made the tank difficult to engage from ground level provided no protection against attacks from above. The composite armor optimized against kinetic energy penetrators coming in at shallow angles was thin and vulnerable when struck from steep angles. The automatic loader that enabled high rates of fire in tank-on-tank combat became a catastrophic weakness when penetrated from above, turning the ammunition carousel into a bomb inside the crew compartment. The aftermath raised questions that military planners on both sides struggled to answer. If the A-10 was so effective, why hadn't Soviet designers developed a similar platform? The answer was complex. Soviet close air support doctrine relied on helicopters for the low-altitude mission. The Mi-24 Hind gunship could carry anti-tank missiles, rockets, and a 12.7mm gun. It was slower than the A-10, more vulnerable, but it could operate from forward positions and provide immediate support to ground forces. Fixed-wing close air support existed. The Su-25 Frogfoot was designed for similar missions, but it lacked the heavy armor and redundancy of the A-10. Part of the answer was philosophical. Soviet military theory emphasized offensive operations. The tank-heavy combined arms doctrine was designed for rapid advances deep into enemy territory. Close air support was meant to suppress enemy defenses ahead of the advancing ground forces, not to hunt enemy armor. The mission profile was different, so the aircraft requirements were different. But part of the answer was also practical. Building an aircraft like the A-10 was expensive. The titanium bathtub alone cost more than some entire Soviet aircraft. The GAU-8 gun system required precision manufacturing that was difficult to scale to mass production. The Western approach accepted higher unit costs in exchange for greater capability and survivability. The Soviet approach prioritized quantity, accepting that individual units might be less capable if enough units could be fielded. The tank versus gun confrontation in 1991 validated the Western approach, at least for that specific scenario, but it also revealed the limitations of both systems. The A-10 was effective against armored columns in open desert with limited air defense, but in environments with dense, sophisticated air defense networks, even the A-10's survivability had limits. The 5 aircraft lost during Desert Storm proved that. Against modern integrated air defense systems with networked radar, long-range missiles, and coordinated engagement protocols, even heavily armored aircraft faced significant risk. The T-72, for its part, proved that numerical superiority meant nothing if the tanks couldn't effectively engage their attackers.